Hello everyone, welcome back. So today we are continuing the thermodynamics series. So in the last session we have discussed about pressure and its measurement, the manometers, various units and the terms like absolute pressure, gauge pressure and atmospheric pressure and the relation among these three terms. So today we are going to learn about another important property known as temperature, and we will state and discuss in detail the zeroth law of thermodynamics, the very fundamental law which is the basis for temperature measurement. So temperature cannot be defined as such. If somebody asks you what is temperature, it's very difficult to explain it with words, right? But you can say whether the temperature is high or low by the feel of warmth or cold. So we can feel it. But whatever we feel with our senses may or may not be right, because in the same room, if you have a wooden chair and a metal chair, the metal object, the metal surface may feel like more cold than the wooden, right? So it is a sense perception of the temperature. But we can say in terms of heat transfer, heat is a form of energy. We have already discussed that, right? So heat is a form of energy. So whenever we consider a system, for example a room, when the windows are open on a hot and humid day, the hot air will be coming from the atmosphere towards the room. The temperature of the room will increase. At the same time, if you use an air conditioner within the room on a hot and humid day, what will happen? The temperature inside the room will get reduced as a result of heat transfer from the room towards the atmosphere, right? So whenever heat is added to a system, the temperature increases. Whenever heat is removed from a system, the temperature decreases. So in that sense, we can express more clearly the temperature difference. Temperature difference is the only means for the heat transfer. If the energy is transferred by means of heat, it is very easy to recognize if whether the energy transfer is heat transfer or work transfer. If there is a temperature difference, that is obviously by heat transfer. It does not mean that there won't be any work transfer. It depends on the process, and the environment. We will discuss about those things in detail later. So the several properties, we are going to discuss about the basis for temperature measurement. So several properties like expansion of some metals or some fluids with temperature increase or decrease. For example, mercury-in-glass thermometer. Whenever the tip of the thermometer is in contact with a hot surface, the mercury column inside the thermometer will start rising until a thermal equilibrium is reached, right? So that forms one of the bases for temperature measurement. So here you can see there is a glass tube and there is a bulb at the bottom, and there is some inner tube, liquid column, in which mercury is filled, right? So this is a mercury in glass thermometer. So whenever this bulb, the bottom of the thermometer, is in contact with a hot surface, this liquid column, that is the mercury, will start rising. So with that example of mercury in glass thermometer, I will explain you the zeroth law of thermodynamics. It is a consequence of thermal equilibrium. You know thermal equilibrium, right? Thermal equilibrium is achieved when the two systems are in contact having same temperature, so that there is no heat transfer between them. There is no heat transfer between two systems or a system and a surrounding whenever there is no temperature difference. We have already seen that heat transfer is a consequence of temperature difference, delta T. So whenever there is no such temperature difference, there won't be any heat transfer. So the system and the surrounding, or two systems in contact, can be said to be in thermal equilibrium. So it was formulated in 1931 by R.H. Fowler. You can see Fowler here. So the statement of zeroth law of thermodynamics is like this. If two bodies are in thermal equilibrium with a third body separately, they are also in thermal equilibrium with each other. If two bodies are in thermal equilibrium with a third body, let us see. Okay. So B is in thermal equilibrium with A, C is in thermal equilibrium with A separately. Fine. B and C do not have any contact. B is in thermal equilibrium with A and C is in thermal equilibrium with A. Now, if that is the case, now thermal equilibrium means B and A are in same temperature and A and C also are in same temperature. So obviously B and C are in thermal equilibrium with each other. That much simple is zeroth law of thermodynamics. Now why this name zeroth law? Because the importance of zeroth law have been recognized on a later time after the discussions and implementation of first and second law of thermodynamics. But later only it was recognized this is the basis for temperature measurement, and temperature is one of the most fundamental property in thermodynamics. That's why it is named as zeroth law of thermodynamics. It should precede the first and second laws. First law states about energy and second law states about the entropy. So the temperature should precede these two properties. That's why it is named as zeroth law of thermodynamics. Now this same thing I will explain you more clearly using this mercury-in-glass thermometer. So there are three systems. One is mercury, second one is this glass tube, the outer glass tube, and the spherical bulb at the bottom, which is in contact with the surface. Okay. Now suppose there is a surface here. One system. System B. System B is the surface where we need to measure the temperature. Now we have the glass tube or the bulb. Okay, glass tube or the bulb. So bulb is in direct contact with the surface. Bulb is in direct contact with the surface. Now mercury is in direct contact with the bulb only, not with the surface. Okay, so mercury in glass thermometer is having three different systems in order to show the temperature in the scale. Okay, we have a system. One system has mercury, another system has this bulb or glass tube, and the third one is the surface at which the temperature is to be measured. Now initially the bulb will be in contact with the surface where they will establish a thermal equilibrium with each other. Fine. Now since the mercury and the bulb is in contact with each other, what will happen? They will establish a thermal equilibrium with each other separately. Fine. So system B is the mercury, system C is the surface, system A is the bulb or glass tube. Fine. B and A and C and A are in thermal equilibrium with each other. So B and C, that is the mercury and the surface, are in thermal equilibrium with each other. That means the rise of mercury column inside will show you the exact temperature of that of the surface. I hope it is clear. Okay. So that much simple is the Zeroth Law of Thermodynamics, and Zeroth Law of Thermodynamics states or defines the property known as temperature, and it forms the basis for temperature measurement. Now let us move on to temperature scales, how to measure the temperature and what are the different units for temperature. So temperature scales are the basis for temperature measurement. So there are two well-defined points in each and every temperature scales, ice point and steam point. You know what ice point is, where the conversion of liquid to, the solid to liquid or back from liquid to solid takes place. In Celsius scale it is 0 degrees Celsius, and the steam point is the point or the temperature at which the conversion of liquid phase to vapor phase or vice versa taking place. In Celsius scale it is 100 degrees Celsius. Now there are two different point scales in SI system and English system. In SI it is degree Celsius. Previously it was known as centigrade scale, but later it is changed to Celsius, degree Celsius. So there should be the prefix degree along with Celsius as well as Fahrenheit. Degree Celsius and degree Fahrenheit. Do not forget that, degree Celsius and degree Fahrenheit. So this degree is needed only for Celsius and Fahrenheit, not for Kelvin. Okay, which we are going to see. Now, temperature scale that is independent of any properties of substance is a requirement. Thereby, the scientists developed in conjunction with the second law of thermodynamics, which defines the transfer of heat from a high temperature to low temperature or vice versa with the help of an external agency. So based on second law of thermodynamics, which is relating the heat with the temperature Q and T in thermodynamics. So they developed a scale known as thermodynamic temperature scale. Again, there are two scales, one in SI system and another in English system. In SI system, it is known as Kelvin scale, and in English system, it is known as Rankine scale. So please note that there is no degree prefixing K or R. Simply you are writing K, uppercase K. It should be uppercase K. If it is lowercase k, it is thermal conductivity. Fine. If you write Kelvin fully as a unit, so you can use lowercase KELVIN. Fine. Now these are the relative values or comparisons of these four different scales: Celsius, Kelvin, Fahrenheit, Rankine. So for example, 0 degrees Celsius, that is the ice point, correspondingly in Kelvin it is 273 Kelvin. Similarly, in Fahrenheit it is 32 degree Fahrenheit, and in Rankine it is 492 Rankine. So there is no degree, there is a mistake here. So there is no degree, 492 Rankine. Similarly, boiling point. Fine. And in absolute zero, in Kelvin and Rankine are, because these are absolute scales. Rankine as well as Kelvin are absolute scales. So absolute zero is represented in Rankine and based on Rankine and Kelvin, whereas in Celsius and Fahrenheit the absolute zero values are minus 273 degree Celsius and minus 460 degree Fahrenheit. Now let us see the relations between degree Celsius and Kelvin, Rankine and Fahrenheit, Rankine and Kelvin, and degree Fahrenheit and degree Celsius. So this you may note down the relationships between two different units. In SI system, Kelvin and degree Celsius are related like this. A temperature T in Kelvin is equal to temperature in degree Celsius added with 273.15. Similarly, in English system, Rankine absolute temperature in Rankine is equal to degree temperature in Fahrenheit, degree Fahrenheit plus 459.69. Similarly, Rankine and Kelvin are related by a multiplication factor of 1.8, and Fahrenheit, degree Fahrenheit and degree Celsius are related by a multiplication factor of 1.8 multiplied with temperature plus 32. Now let us see an example of a temperature rise of 10 degrees Celsius. Suppose the temperature of a substance during a process compression process. Obviously, compression process only the temperature will rise. During expansion process, temperature will lower, right? So how to express that temperature rise? For example, if the initial temperature T1 be some 10 degrees Celsius, the final temperature be 20 degrees Celsius. So there is a temperature difference delta T of 10 degrees Celsius. How to express these 10 degrees Celsius in Kelvin, degree Fahrenheit and Rankine? It is not 273 plus 10, 283 Kelvin. That is wrong. If delta T is given, the temperature rise from initial temperature to final temperature, delta T in degrees Celsius and Kelvin are same. If it is delta T is 10 degrees Celsius, in Kelvin also it is 10 Kelvin. Let us see how that is. Let the initial temperature be T1 and the final temperature be T1 plus 10 degrees Celsius in Celsius scale. So that is a heating process. Now in Kelvin scale, the initial temperature is T1 in degrees Celsius plus 273.15. The final temperature is T2 in degrees Celsius plus 273.15. What is T2 now? T1 plus 10. So T1 degrees Celsius plus 10 is the final temperature, that is T2 plus 273. Now what will be the delta T? T2 minus T1. When you subtract T2 in Kelvin minus T1 in Kelvin, you will get delta T in Kelvin. So that is same, 10 Kelvin, right? So when you do the calculation, you can see T1 will get cancelled out, 273.15 also will get cancelled out. So only 10 remains. So delta T in Kelvin is same as delta T in degrees Celsius. That is the first conclusion of temperature difference in different scales. In SI system and English system, that is SI system, relative scale and absolute scale, the relation for temperature difference is same. Delta T in Kelvin is equal to delta T in degrees Celsius. Similarly, in English system, absolute scale Rankine and relative scale delta F, the delta T will remain the same. Now, also, if you proceed in a similar way for the same temperature difference delta T of 10 degrees Celsius, you can finally find out, you will arrive at this relation, delta T in Rankine is equal to 1.8 times delta T in Kelvin. Thereby, you can express the temperature rise in the above example as 18 Rankine and 18 degree Fahrenheit. Got it? So, through this example, we have concluded these three results. Delta T in Kelvin is equal to delta T in degree Celsius, delta T Rankine is equal to delta T in degree Fahrenheit. Also, we have delta T in Rankine is equal to 1.8 times delta T in Kelvin. Absolute scale relations. Fine. I hope it is clear. If you have any questions in this session, please use the comment section below and post your questions. And don't forget to subscribe to get notifications on new videos in mechanical engineering subjects, fundamental subjects. Also, please like and comment, share with your friends. Thank you for watching. Have a good day. Bye.